Typically, databases require a hierarchy of power. Administrators can make changes that regular users can't. But using proof of work to validate and secure a database means that it can be owned by everyone and no one at the same time. Hi, I'm Amy James, and welcome back to What Kind of Internet Do You Want? Today we're talking about something that is so essential to Web3 that it wouldn't exist without it, and that's proof of work. In this video, we're breaking down what it is, the important benefits it provides, and of course, discussing some of the problems it faces as well. But before we start, please remember to like, subscribe, and share, and let's get into it. A key aspect of Web3 is decentralization. In the current model of Web 2, most of what we do online is controlled by centralized internet giants like Google, Facebook, and Amazon. And every time we interact with them, they get more and more data that they can use to make money off of us. And it's true. We get a lot of cool services in return, but it comes at the cost of our privacy and our autonomy. And that means that large corporations and governments get to hold, own, and really control details about what each one of us does, thinks, and buys online. And we have to trust them to safeguard that data from hackers and not do anything unethical or exploitive with it themselves. And as we've talked about before, despite the best intentions of most Web 2 platforms, it's the centralized structure of the system that depends on surrendering our personal data and makes the networks so vulnerable to attack. Web3 fixes this because it's decentralized and user data is private and secure. The most well-known technology that makes it possible is, of course, blockchain. Blockchain was invented in 1991 by Scott Stornetta and Stuart Haber, but it didn't have the potential to restructure the web until it was combined with proof of work. So what is proof of work? To explain, let's go back in time to 1997 when British cryptographer Adam Back invented one of the first implementations of proof of work. It was known as Hashcash, but it didn't have anything to do with money. It was a way to prevent email spam. Back's idea used hashing, a form of cryptography where an algorithm turns any piece of data into a unique number of a predetermined length. It's called a hash code, or more commonly, a hash. What's really amazing about hashing is that while the numbers appear to be random, they're totally unique to the particulars of the data that's being used. So if another person fed the same input data into the hashing algorithm, they'd also get the same resulting hash. And if you changed even a bit of the data, one word of the email, even a single letter of the email, the algorithm would produce a totally different hash. The way it worked was that before someone could send an email, their computer would take all of the pieces of data from the email, the to, from, subject, body of the email, etc., and combine it with a nonce, which is a seemingly random number, and then run them both through the algorithm to create a hash. The computer would repeat this with a different nonce each time until the resulting hash had a certain number of zeros in front. And then the successful hash was sent with the email as proof that the sender had done some amount of actual time-consuming work. Meanwhile, the receiver could check to make sure that the hash had the right number of leading zeros, which is a measure of the compute cost needed to send it. The same way that the post office checks to make sure that a letter has the right amount of postage. But how's that supposed to help with spam again? The idea was that for individual users, the small amount of compute power needed to find the right hash would only delay the email by a second or two and cost next to nothing. It would be virtually unnoticeable. But for spammers who send out hundreds of thousands, even millions of emails a day, the time delay and cost involved would make spamming completely unprofitable. And this is particularly relevant these days when we've taken for granted that email is a decentralized protocol and that the spam problem has been largely fixed, because Unfortunately, the solutions that the tech industry used instead of Bakkt's approach ended up turning email into just an oligopoly run by a small handful of trusted email providers. And I don't know about you, but I still get tons of spam anyway. So unfortunately, as brilliant as it was, Bakkt's solution didn't catch on, at least at first. About 10 years later, an anonymous cryptographer known as Satoshi Nakamoto built on Bakkt's idea to create what we all know today as Bitcoin. A big difference with Bitcoin is that it uses proof of work to protect a shared database, where Hashcash was used at an individual level. Typically, databases require a hierarchy of power. Administrators can make changes that regular users can't. But using proof of work to validate and secure a database means that it can be owned by everyone and no one at the same time. Nakamoto's idea was that anyone could compete to create proof of work in order to secure a decentralized ledger, for which they would be awarded bitcoins. With this system, computers, usually called mining nodes, compete to do 3 things. First, they confirm that the previous winning hash was mathematically valid. But wait, how do they do that? Well, think of it this way. Do you remember Sudoku, the number game that everyone was playing a few years ago? In classic Sudoku, there are 9 big squares with 9 little squares each. The player needs to fill in the little squares with numbers in such a way that every big square, every row, and every column contains the numbers 1 to 9 without any duplicates or omissions. Sudoku is a puzzle that is very hard to solve, but very easy to verify. You can easily see if the numbers are wrong. Likewise, it's very hard in that it takes a lot of wrong guesses for miners to find a valid hash for a given block, but it's very easy to verify that the winning hash was valid. They just run all of the inputs as well as the nonce that the winner used back through the algorithm, and if the output is the hash that the winner claimed, it's valid. The second thing they do is check and validate that all of the network transactions that have taken place since the last verification session, aptly called a block, and enshrine them in a new block in the chain. With Bitcoin, the transactions are movements of existing Bitcoin. So validating them simply requires that the miner confirm that the signature of each sender is valid and that it was generated by the private key corresponding to their public key. And if you missed our video on public key cryptography, we'll link it here and in the description below. They also validate that each sender has enough of a balance of Bitcoin in their public ledger to make the transaction in the first place. It's basically like your bank confirming that your account has the money and that your signature is valid before cashing a check. The third thing they do is produce their own proof of work by generating an enormous number of hashes as fast as possible in hopes of arriving at the valid hash before anyone else. At the moment, up-to-date mining rigs can produce 110 trillion hashes per second, and the average number of hashes they must produce to find a valid one is this number. We call this process trustless verification because it doesn't rely on any one centralized trusted authority to determine its authenticity. Instead, the transactions are trusted because about 1 million Bitcoin miners have all independently verified them. So in this way, everyone that's competing on the network must come to consensus that the previous block is correct. This process is completely decentralized, and it ensures that every transaction on the blockchain is valid and no counterfeit Bitcoin are sent. Now, in theory, a malicious party could amass enough computing power to beat out the entire network of miners and use that advantage to verify fraudulent transactions. This is known as a 51% attack because the attacker would need to have more computing power than 51% of the network in order to have a chance at pulling it off. But they would have to win the next round and the next round and the next round and so on. Otherwise, other miners would notice the fraud and invalidate their wins. And it would cost the criminals around $40 billion in newly produced mining hardware and more than $1 million in electricity per hour to keep up the ruse. So it's not a great way to make a buck, especially since as soon as the attack ended, the honest miners on the network would invalidate anything they accomplished. There has never been a 51% attack on the Bitcoin blockchain, and some game theorists argue that at this point, it's really unlikely to ever happen. So proof of work doesn't just prevent spammers and crooks from taking advantage of innocent users, it provides an entirely new framework with which to approach ownership of the web by incentivizing many independent parties to spend their time and money verifying the truth. Nobody, and yet everybody, becomes a controlling authority. It's really what Web3 is all about, but it can't be all perfect, right? You may have heard that proof of work uses a lot of energy and is contributing to climate change. You may have also heard that it's relatively slow and inefficient. And as a result of these problems, there are many people in the crypto industry working to develop alternatives. The most well-known is called proof of stake. But there are many others like delegated proof of stake, proof of burn, proof of capacity, expected consensus, and succinct proofs of random access, and many more. And we're going to cover some of these in more detail in upcoming videos. But for now, I just want to note that more than half of Bitcoin mining is already run on renewable energy, and lots of it is run on what is called trapped energy, sources of energy which would be impractical to connect to the grid and would otherwise go to waste. Proponents say that Bitcoin and other cryptocurrencies are actually helping to drive the improvement of energy-efficient computing and incentivizing investment into clean energy sources because it helps to bring down their costs. No doubt this debate will rage on for a while, and the Web3 community will continue to weigh in on what kind of internet and what kind of world we want to build. And if you found this video helpful, please hit the like button, subscribe to the channel, and share the video. You can find me at Amy of Alexandria and follow the Web3 working group at Web3WG. Thanks for watching, and I'll see you next time.